from the midterm. The reason we're doing this problem from the midterm is there's like a kind of a meta proof idea in this that we'll use in our main proof from the textbook. So this was the problem about you have a sequence of the xn's. Those are the original sequence. The xn's converge to 0. So if the xn's converge to 0, then the averages of the xn's also converge to 0. So this is a really good one to test if you know what convergence of sequence is. Like, what does it mean? Because the sequence is sort of complicated, okay? And this, you have to be able to analyze this specific sequence. So let's see what it looks like. So really, it's all about this sequence. So the a, n are the average 1 over n times x1 plus x2 plus dot 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 plus xn. Let me write a few more because it's nice to see a lot of them. Let's do a few more here. x3 plus x4 plus dot dot dot. All the way up to, let's do xn minus 1 plus xn. Okay. So it's a big old sequence. And when you look at this, you're saying, okay, I want to prove that this thing is going to 0. So I would like to show, we want to show that the norm of the an is getting small, is going to 0. It's small. I'm just going to write is small. You can think of it's going to 0 or it's less than epsilon. But this is like in my brain, this is how I'm thinking about it. Because like, you know, in my day-to-day experience, I'm used to thinking about small things. So this is like nicer for my brain than less than epsilon. So what would stop us? Well, okay, if I take the norm here, I do the norm of everything, the norm of the an, then I do the norm of all this, okay? And then by triangle inequality, I can actually move this inside. So I can do, I can write it like this. Let me add. Let's make a little bit more room, and then I can do it properly with lines. Okay, so this is less than or equal to by triangle inequality. By triangle inequality, 1 over n. And then I can put the norms on all the individual guys. Let's do that. Plus norm of x2 plus dot dot dot. Oh, I said I would keep a few more around. Okay, let's keep a few more around. Plus norm of xn. Okay, with a big bracket. Okay, one thing that can go unfortunately wrong is if you get your inequality backwards, then everything will go wrong. So it's good to double check that you have it the right way, but I think I do have it the right way here. And we want to prove that this is small. So if these things individually were small, then I would be happy. Okay, so we gotta bound this big sum. Now here is the issue, and I think this is another way to think about problems, is what is stopping us from proving the thing that we want? So these are like our issue, our liabilities. Okay. And I actually think we have two issues. One issue is there's a lot of these terms. There's n of them. So this is issue number 1. Too many terms. Too many terms. And in fact, there's n of them, right? And so the thing that we have is that the norm of the xn's is small. So the norm of any individual guy maybe is small, or like this last piece is getting small, but there's n of them, and that's bad. You see? So if you did some kind of bound and you were just like, bound these, there's n of them, that's going to be bad. Of course, we have a 1 over n to sort of save us, but if it was like 1 over n squared, then maybe n things wouldn't be so bad, but n things with the 1 over n is like just enough to not help us, right? So there's too many terms, there's n terms, and we only have a 1 over n here, so this is like an issue. So that's one problem. And then there's another problem, which is kind of, also related to this thing, is that these first terms, even though the xn's are small, that's as n is large. So when n is really big, the xn's are small, but x1 is always on our stupid sequence, right? So the first couple terms, it's not that they're small. The first terms could be really big, right? So maybe the last terms are small, but the first terms are big. So x1 does not go to 0. Does not get small. Okay, so these are our issues. We have a lot of terms. We have terms that are annoying, and we have to somehow be able to still solve it. Okay, and this is a kind of common issue that will happen. You're going to see we're going to have the exact same issue in what we're trying to prove about integrals. Later on today, we're going to have the same kind of double issue phenomenon. There's a nice trick for this kind of thing, or like a kind of a meta strategy you can do. If you have two problems, we got too many terms, and we got big terms, how can we actually, deal with our two problems? Any ideas? Yeah.
Maybe you could split it up into two groups. The latter half are all small enough, and the first half, there's how many of them?
Yes, that's right. That's very good. So basically, we're looking at the sequence, and the sequence has two issues. And we can't solve both issues at the same time. Both issues together like make each other worse because there's a lot of things and each individual thing is big. But if we take our big sequence, we cut it into 2 parts, we can cut it into 2 parts so that each part has only 1 issue, okay? So instead of having 2 issues for the whole thing, we got 2 halves, and each half has only 1 issue instead of 2 issues. And then this is like a sort of a divide and conquer strategy. So this is going to be the idea. And this is sort of a meta idea that comes up a lot. Idea, divide into 2 groups, and each group will only have 1 issue. Each has only 1 issue. Okay, so you go from 1 big long sequence that has 2 problems to 2 sequences, each of which have only 1 problem. And so, like very roughly speaking, the idea will be to just make some cut somewhere over here and call this the beginning of the sequence. And the beginning of the sequence has the problem that the terms are big. And then we have the sort of tail of the sequence. And the tail of the sequence has the problem that there's a lot of them. But if we choose the tail far enough out, we can make sure that each individual term is small. So this is the thing. So we'll cut it into 2. So this is like the tail, and the tail, there's a lot of them. There's too many terms in the tail, but each individual term is small. And then this is the front, or the head, if you want, I don't know, the head. And the front, they're all big, but there's only a few of them. And then when there's only a few of them, we'll be able to use this 1 over n to save the day, okay? So as long as there's not too many of these, this 1 over n will save us. That's the idea, okay. Once you have this idea, you gotta write up a nice proof. I'm gonna do that. I'm trying to think if it's instructive to go even more in detail than this. This is the big idea. I think from here, I'm just gonna jump into a nice proof. You could play around with like, actually, okay, here's one thing we can do. Let's do one nice line. So this is the idea to divide into 2 groups. So 1 over n, excuse me, times the sum of x1 plus dot 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 plus xn. So for any fixed, let's fix my favorite number m. Okay, we can write this as the sum of the first m. So 1 over n, and then we do the sum of the first m. And then we do the rest. Xm plus 1 all the way up to xn. Okay, and so the idea is in the first few, there is some, maybe each individual term is big, but this 1 over n is going to save us. And so the thing I'm going to bound it by is the maximum of all of these things. The maximum of all of these things, which is some sequence of maximums. And there's m terms, so I also got to multiply by m, right? So all of these terms individually are less than the maximum, and there's m of them. And then the thing that is going to save us is that we're dividing by n. So even if n is a big fixed number and the maximum is a large number, eventually this divided by n will save us. On the tail, it's the opposite problem, right? So on the tail, it's the opposite problem. There are many, many, many terms, but all of them are hopefully very small. So we want them to be very small. So why don't we go back now and actually say, instead of affixing an m, why don't we say let m, let's go back, and we'll choose m so large so that k is less than epsilon for k greater than m. And then even though there's a whole whack ton of terms over here, like getting larger and larger, getting close to n terms, like lots of them, every individual one is less than epsilon. And so I can say this is less than epsilon times the number of terms is n minus m. Okay, and this is all, again, divided by n. And now, this divided by n is not really helping me. I can just bound this by saying, okay, there's less than n terms over here. And then I'll get that. Okay, so it'll be less than or equal to m times the maximum. And then we'll do x1 to xm divided by n. And then over here I have epsilon. So I bounded n minus m over n is less than 1. Okay, you put that in nicely, since n minus m over m is less than 1. Okay, very nice. Okay, and now you can kind of see as n gets bigger and bigger, this will eventually be small. Okay, here's another fact that we need. If m is some big number, you might be worried that this is getting larger and larger, but this is actually some bounded thing, right? This is some sequence, so it doesn't matter how big this is. As long as it's a finite number, which it is, we're going to be okay. So all I got to do is find, let's call it, I used M already, let's call it capital N, so that if N is greater than capital N, then all this stuff is small. The maximum of x1 to xm over n is less than epsilon. And you could say this is okay since the limit of the left-hand side is 0. So the left-hand side is getting closer and closer to 0, so it's eventually less than epsilon. Okay, and then for n greater than the maximum of n comma m, right? So as long as n satisfies the first thing that we did over here, I guess this was only true for things larger than n, for m. For n greater than m, because the way I split it up. Then we have both things are true. Then what we are working on, okay, let's give this a name. Let's call it heart. Heart is a nice one, heart. Then heart is bounded. Oh no, it's a triple heart. That's okay. It is bounded by, and then you say less than or equal to dot 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 of heart, continuing our inequality, is less than or equal to epsilon plus epsilon. Okay, so right, the first bit, when n is really big, this is less than epsilon. That one's always less than epsilon, and so it's less than 2 epsilon. So now you could make some argument about 2 epsilon, but it's actually, I think it's easier to just go back. And every time we chose epsilon, actually choose epsilon by 2. So just to divide it by 2 here, this will be divided by 2, and then this will be epsilon divided by 2. And then over here, make this thing less than epsilon divided by 2. And then we get epsilon over 2 plus epsilon over 2. Okay, and so the whole thing equals epsilon. And then we say, since epsilon was arbitrary, the limit as n goes to infinity of the an equals 0. And then maybe you go back to the very beginning, as I think I just started doing an epsilon, I never said it. So given any epsilon greater than 0. Any epsilon greater than 0, all great proofs start with given any epsilon greater than 0. Okay, so there's your proof. It starts here, and then goes from there. Okay, very nice. Okay, this is a really common proof technique. You have problems, and you separate your problems. You have one area where you can do one thing, you have another area where you can do another thing, and each area is sort of bounded by its own separate argument with an epsilon by 2, and at the end they combine together to give an epsilon. Questions or comments about this one? Lots of people actually did get this one on the midterm, which is great. It was a homework problem from the textbook, so maybe you thought about it there, or maybe you just came up with the vague idea. But yeah, it was pretty well done, actually. Okay, so this kind of thing has a name. Some people call this an epsilon by 3 argument, this proof idea. And it's very common that you have 3 parts. The reason you have 3 parts is often you have the thing you want, and then you have the limit that you want. And to prove that the thing you want is close to the limit, you go up to some other thing. And the other thing is close to its other limit. And then the other limit is close to the limit you want. And each of these is like an epsilon by 3. So this is like a common proof technique of you have sort of 3 sources of error that are all coming from different things. The thing you want is approximated by some other thing, that's some source of error. The thing that you want is conversion to some limit, so it's getting within epsilon by 3. And then the other limit is close to the limit you want, so it's epsilon by 3. This is the kind of thing. You take your argument and you divide it into 3 separate pieces and do it. The way you remember this is there's a beautiful comic that I have over here. Okay, this is an epsilon by 3 argument where the epsilons are fighting over something. I don't know. Excuse me, I beg to differ. Fools! Okay, epsilon over 3 arguments. Now you will never forget it. It's a common proof idea. This is from the excellent webcomic Brown Sharpie, which by the date you can figure out when I was an undergrad. Brown Sharpie. Very nice. Okay, so that's kind of our warm-up problem, and we're going to use this technique on our next proof. What are we doing in this course? So this was in the Tuesday, Thursday. Last time we did the no free lunch theorem. The no free lunch theorem is stated in terms of sequences of intervals, but really you can convert those into integrals like I did over here. And what it's saying, let me add in the sum over here, n equals 1 to infinity. We're saying if you have this kind of thing, then you have this kind of thing. So if your intervals, they converge, you have a bunch of intervals, and there's infinitely many of them, and the intervals together make up one big interval, then the limit of the sum of the integrals equals the integral of the limit, right? So it's saying that intervals are cool with limits, like they don't do any weirdness. And this seems very obvious, but like we talked about last time, it's something special about the real number line, right? It doesn't work for rational numbers. It's something that requires proof and requires like the completeness of R and like compact sets and all that. That was what we proved last time. I know the proof is like somewhat complicated, but the statement is the part we're using today. Any questions or comments about the statement, or what is it actually saying? Okay, and I kind of called it the no free lunch theorem, because it's like you take an interval, you chop it up into pieces, there's no like extra piece floating around, right? Like it does what you think. When you chop it up into pieces, even if there's infinitely many pieces, it does what you think, right? The sum of the integrals equals the integral of the sum and all that. Okay, so that's what we did last time, and we're going to use that today to prove this theorem. So this is the main theorem we're going to do today, theorem 2.2.6, that says if you have a non-increasing sequence of non-negative step functions. Okay, these really annoy me. Non-increasing like explodes my brain because like it sounds bad. So I always replace non-increasing with weakly decreasing, because that's what it's doing. So the sequence is decreasing, but it's allowed ties. Like it could stay flat, right? Non-increasing to me sounds like, I don't know, it's like my brain just slips out from the double negatives. Okay. Non-negative step functions. Non-negative I've gotten used to, but for many years I would say positive, weakly positive. Let's do weakly positive, okay? So they're positive, but they're allowed to be zero, okay? That's what non-negative means. So they're decreasing, and they're all positive, and they go to zero for every x. So they go to zero pointwise. So here's what the functions look like in this here. So what the fn's look like. So they're decreasing, and they're going to zero, and they're always positive. So they're kind of like trapped in the upper y-axis, and they're step functions, so maybe they look kind of like this. I don't know, here's one of them. Some function like that, so maybe that's f1, and then f2 is like this. So it's allowed a tie, but it can't get bigger. So here's f2, and then f3 is some other one. Okay, I don't know. And over time, at every individual x point, they go down to zero. So if you live on the x-axis and you are at some individual point, then pointwise, it looks like the functions are coming down to zero at where you are. Now, of course, this is the tricky thing, right? Pointwise convergence doesn't mean, for example, the maximum height of the f's could always be 1, right? So it could be that they do this tricky thing like we talked about in class on Tuesday, is where like the height is always 1 here, and then just like it's getting narrower and narrower, right? And then so for every individual x, it goes to 0, but the height of the function is always 1, and that's what makes the problem hard. If there's no like global bound on the f's, it's just for every individual x. The conclusion is that if the f's go down to 0, then the integrals of the f's go down to 0 too. So fn's go to 0 pointwise. And the conclusion, so if the fn's go to 0 pointwise, in the special way set up by the theorem, right? They have to be positive, they have to be decreasing. Then the integral of the fn's goes to 0 too. Okay, so, kind of like the averaging problem we did before. We have all the individual terms are going to 0. The integral is kind of like the average, that also goes to 0. That is the theorem we're proving today. Again, seems kind of obvious, but requires proof because of these tricky things. Yeah?
I'm confused about like the point where you have like all of the things starting. Like, why doesn't that one also go to 0?
You mean over here?
Yeah.
So, So I guess I was trying to make an example. Because if you kind of think of the functions going to 0, your first brain is like, oh, it's like a big hump, and then like they all come down to 0. And then the maximum, you're thinking the function's getting close to 0, as in like all the functions are getting squeezed to 0. But what I was trying to draw over here is that there's another way they can go to 0, which is that at every individual point it goes to 0, but the like height of the function is always 1, and it's just like moving out of the way. This is a little bit like problem 1 on Tuesday, right, where we had the interval from 1 over 2 to the n to 1 over 2 to the n plus 1, and like you stack on more and more of these, so the height is always 1, and they kind of like slide over to cover everything, and that can happen here. So that's why I was trying to draw the sort of like bad thing that can happen, which is that there's no global bound on the functions. Like you can't say the functions are going to 0 in height, in norm, but you can say they're going to 0 pointwise. And that's what I wanted to include in my picture. Yeah, does that answer your
Sort of.
question?
I'm just confused about like if it goes to 0 pointwise, then like doesn't it have to go to 0 at the point?
Yeah, okay, but I guess the point is that it can slide out of the way. Let's do an example. Yeah, no, I think this is a great point. Let's make an example. What if we do, let's make fn, let's make it the indicator function, just like we did in class, and I'm going to pick two numbers that are sort of like smooshing in together. So let's do 1 plus 1 over 2 to the n, and then let's do, okay, I think I want to do 1 plus, maybe I don't want to do 1 minus something. What do I want to do? I want to do 1 minus 1 over 2 to the n. Okay, if I'm going to do that, then I'm going to make this one just 1. Okay, that way it works. Okay, so this is the example that is similar to what we did in class. Yeah, okay, so these things around 1, around x equals 1, they always have their peak including x equals 1 and then a dotted line. So literally at x equals 1, the function is 0. So fn of 1 equals 0. And fn looks like a little peak like this, and the width of the peak is 1 over 2 to the n, right? And these things, they do converge to 0 pointwise. So fn converges to 0 pointwise, fn to 0 pointwise. And the reason is the same reason as on the Tuesday problem, which is that at any fixed point, eventually the 1 over 2 to the n will pass you by, right? So if you're really close to 1, you're like 0.99. At x equals 0.99, as soon as 1 over 2 to the n is less than 0.01, the peak is past you and you're literally 0. Yeah, so these things go to 0 pointwise, but their height is always like 1, and so when we do our proof, we're going to have to deal with that. Of course, the conclusion of the proof is that the area of this is going to 0, and that's totally fine too, because you see that they're shrinking. Yeah. Yes?
So that function is increasing though, right?
No, it's okay, this is a very good point. The function itself, as a function of x, is an increasing function. When they say over here that the functions are a weakly decreasing sequence of functions, they mean as a sequence of functions. So that's a very good point as well. So fn, if you look at fn of x as a sequence for x, so you look at f1 of x, f2 of x, f3 of x, then it's decreasing this way, weakly decreasing. So for any individual x value, they're like coming down, right? They don't like turn around and go back up. Yeah?
If we define our fn's to be the indicator function of negative infinity to infinity, excluding the interval, like, say, minus n to n.
Yeah.
Oh, that closed interval, never mind. Closed interval, open bracket to infinity, then every
Yes.
single time we take one of those intervals, we get an infinite area under the curve.
Yes, that's right.
So how would that converge
Yes.
to 0?
Yeah, the way it converges to 0 is step functions have to be made of finitely many pieces, each of which are finite things. So a step function can't actually go to infinity. Yes, but this is an important point. Like if you start allowing things at plus and minus x's plus and minus infinity, your life gets significantly harder and more complicated. And so it's very important for us that we're starting with step functions that have some actual bounded domain. Everything we're doing in the course, essentially at this point, you could think of everything lives on 0, 1, right? So in the book, they let it be arbitrary. They're like, just pick any interval you want. But what we're doing is essentially, you have some bound, like a lower x value and an upper x value, and we're only doing things from there to there. And then once you have that, you can sort of increase slowly. Once things work there, you'll be able to upgrade. But that's an important point. We're not dealing with the x's being infinity. Yeah, great point. Yeah, these are fantastic questions or comments, by the way. Anyone else? Okay. So that's what we're going to do. We're going to prove this, and you're going to see that it's a same kind of epsilon over 3 argument of dividing it into several pieces. Before I go into that, just so you see the roadmap, the point of proving theorem 2.2.6 is it's going to allow us to prove that our definition of the Lebesgue integral actually makes sense. So when you have a function, if you write it out in two different ways, so you write it one way as the sum of the fn's and one way as the sum of the gn's, then actually those two things have to add up to the same infinite limit, and it's going to use exactly this kind of thing. It's going to use the fact that we obey inequalities. If you're going down to 0, then the integral is 0. And the way to look at it is to look at the difference between the fn's and the gn's. The fn's minus the gn's will be going to 0 because they're both adding up to f, And so the integral of the fn's will, minus the integral of the gn's will also go to 0, and then we'll be happy. So this is like essentially, this is used to prove this. That's why we're doing it. Used to prove this. Okay, and so that's what we want to get to, and that's why it's an important theorem. Okay, what is the technique of the proof? So the reason I drew this kind of picture is to show you, again, there are two issues with the f's, just like in our warm-up problem. The f's have one problem, which is that the height of the f's might be very high, right? There's no reason that the maximum height of any f's is going to 0. The maximum height of the f's might always be a big number. That is exactly like the x1s earlier in the warm-up, right? The front of the sequence maybe has lots of big numbers in it. On the other hand, for everywhere else, the function eventually has to go down to 0, so there's going to be sort of like most of the function has to be close to 0 eventually. So there's sort of two regions, and it's exactly the same kind of regions as we did in the warm-up problem. There's one region where the function is very tall. This is like problem number 1. And then there's another region where the function is close to 0. And that region might be very wide, okay? So we sort of have two problems. The function f might be very tall, and it might be very wide. But we know it's going to 0. So the wide bit can be, we can capture it within some like really small, super thin rectangle, right? Long, but very thin, and then we'll be okay. And then the tall one is thin the other way. Okay, it's going to be very tall, but we're going to make sure it's really, really skinny. And then each of these will be bounded by epsilon over 2, and then we'll be happy. So it's kind of a similar idea to the original thing. Let's get into the proof. Okay, so here is the proof. Proof of theorem 2.2.6. Okay, let me also get my notes here so I keep it relatively in order now that we have ideas. And so the first idea is to define some sets. We're going to let an be the set. Okay, I think I also make some suppositions. Okay, we're going to let AB be an interval that covers everything, that supports, let's say supports all the fn's. And notice, in general, if you have an infinite sequence, maybe the interval is getting bigger and bigger, but because the functions are decreasing, they're all supported on whatever f1 supports. So because fn's are decreasing, the support of f1 is good enough. So in other words, you draw, like we did in our picture, whatever f1 is, f1, wherever it's non-zero, that's where all the action is happening. If f1 is 0 somewhere, all the other functions have to be 0 there too. We're going to call that interval AB. So I guess we could even label it on our picture. Right? This is A, and then this is B, and nothing can happen outside of AB. Okay, that's very good. And then we're also going to let the maximum of f1, we're going to call that m. Let m equal the maximum value of all x of f1 of x in absolute value. And again, it's a maximum because step functions achieve their maximum. In general, a function doesn't have a maximum. It has a soup. But because it's a step function, it has made of finitely many pieces. And whichever piece is the largest, that'll be the maximum. And this maximum is also the maximum over all x, over all the f's, over the maximum over all n of fn of x, over all possible fn's. And the reason, again, is all the fn's are less than f1. They're weakly decreasing. It can't be bigger. So if you bound f1, you bound all of them. So m is the maximum height, max height, and this is the max width, the max width. Okay, and then we're going to argue from there. And the first step is to define the sequence of sets. We're going to let an be the set of all, no, first we're given an epsilon. Oh yeah, it must be given an epsilon. Okay, let epsilon greater than 0 be given. And we will find an n naught such that the integral of f of n naught is less than epsilon. That's our goal. We're looking for some element of the sequence where it's less than epsilon, and then notice, because they're decreasing, notice integral of fn less than integral of fn naught less than epsilon for all n greater than n naught, since they are decreasing weakly. So the integrals can't go up. They can only go down or stay the same. I guess this could be a less than or equal to. So once we find a single guy who's less than epsilon, then all the other ones past that point will also be less than epsilon. Okay, and now we're ready to sort of start defining. Remember, our idea is to capture these two different things. And one of them, we want it to make it less than epsilon over 2. So we want the area in this big thing to be less than epsilon over 2. So what should I make the height? The height over here is going to be epsilon over 2b minus a. That's going to be the height of this little shaded blue region. And if the height is less than epsilon over 2b minus a, then no matter how much of it is in there, the total area of everything in the big rectangle will be epsilon over 2b minus a times the width b minus a, which will be epsilon over 2. And then we're going to have a similar idea over here. We're going to make this thing, this width will be epsilon over 2m, because the height of this function is m. Okay, so this is all just ideas, and I don't need to tell you about this now. It's going to come up in the proof, but just to see how we're going to bound these two rectangles. And so we're going to start by doing this wide rectangle. And to start doing this wide rectangle, we're going to look at the set of all points where you're in the rectangle. So let an subset AB, this is where are we inside the rectangle. And so this will be an equals the set of all x values such that fn of x is in the rectangle, and in the rectangle means its height is less than epsilon over 2 b minus a. Okay. So it's the set of all points where the fn's live under this rectangle. So I can go back to my picture and draw it in, right? So for f1, the set a1 is only the points out here. This is a1. Okay, but then a2 is a little bit bigger. a2 is all these points, because you see the function f2 went down a little bit, and then a3 is even bigger, right? a3 is the next all the way up to here. So as soon as the function enters the blue rectangle, that's the set A. It's the set of points where you enter the rectangle. Maybe there's parts of A over here as well. So A doesn't necessarily have to be just one chunk, but some set. And it's whenever the functions, when they fall into our blue rectangle, then we're happy. We're like, yeah, you're in the set A. You're a good. I would have called it G for good, but okay, we're calling it A because that's what the textbook did. So the ANs are increasing in the sense that they are subsets of each other. So since the FNs are decreasing, the ANs increase as sets. So in other words, you have A1 is a subset or equal to A2 is a subset or equal to A3, and so on. Okay, so they're getting bigger and bigger and bigger. And not only are they getting bigger and bigger and bigger, eventually they cover everything. So this is eventually going to be sort of getting closer and closer to the set AB, which is the biggest thing. What are we going to do with this? We're going to look at the differences between these and see what those are. So we're going to define Bn to be the difference between these things. So for example, we're gonna make a set that is the difference between A2 and A1. I think they call that B2. They call it B2 or do they call it A1? B1. Let me see. Bn. Okay, this is called B2. So B2 is the difference, the set difference A2 minus the set A1. So you take A1, you add on B2, that is some positive amount of stuff you added on, and then you get to B2, and so on. So B3 is the amount of stuff. This is A3 minus A2, and so on. And so by doing this, any AN is actually, it's the union of all these B's, and the B's are disjoint. So it's the union from K equals 1 to N of the BKs, and the BKs are disjoint. BKs are disjoint, they don't overlap, right? Because we add them in little by little, and they're defined as this difference. So if you want, the definition is Bn is defined to be An minus 1. Let me erase this definition equals for people who don't like that. Okay, so define the set. Okay, what is the point of doing this? The point of doing this is now we have all these disjoint intervals, and we can apply the no free lunch theorem to them. Question over here, yeah?
Doesn't the union of all the B's skip over the points that are in A that aren't? Oh, well, I guess.
Oh,
Okay.
I think you might be right that maybe I forgot A1, right? So maybe what we should do is we should define B1 equals A1. So B1 is A1, and then B2 is like what you have to add on. And then that way, if you want to get A3, you do B1 plus B2 plus B3, and then you get A3. So yes, maybe I forgot this one. So B1 equals A1, and then Bn equals this for n greater than or equal to 2. Yeah, great point. Question in the back, yeah.
When you do the epsilon, like the fn's are less than epsilon over 2
Yeah.
b minus a, is that something you have to know going into the question, or would you find that out and then go back and change it?
Yeah, this is a good point. I think if you were discovering this organically, you would probably start with an epsilon, and then later on in the proof where it's going to get multiplied by b minus a. The way I'm trying to present it, I was trying to tell you guys this idea with the two boxes, and then it's sort of intuitive that it should be the height of the box. But you're right that in real life, often you're just like, small number, and then at the end of the proof, you're like, put together all the small numbers. So yeah, that's a good point. Yeah?
For that picture, where are the
The
B's?
B's are the differences between the A's, right? So like I drew this little red area as A1. The purple area is the A2, that includes A1. And the B is like what you have to add on to A1 to get this. So it's like the purple area minus the red area. This might be way too small for you to see. Here, hold on. Guys, the magic of modern technology. Okay, so right? Okay, let me properly fill in the green one, which I did not do. So the sets are getting bigger, right? A1 is up to here, A2 is everything up to there, and A3 is everything up to there. And the B's are just the differences, like what you have to add on. So B1 is this, B2 is just purple but not red, and then A3 is green but not purple, and so on. So it's like the sequence of things you have to add together to get the A's. Okay, and so the reason this is going to work is our no free lunch theorem says if you have these disjoint sets and they add up to everything, which they do eventually, then their individual sizes have to be small, which is what we're going to use. Yeah, great question. Anyone else? Okay, let's go back to normal zoom and go down. Okay, so this is the observation is we should be able to apply the no free lunch theorem to the B's. So notice, since the fn of x goes to 0 pointwise, the B's altogether cover everything. So say the infinite limit of B's is everything. And in an equation, so that's the sort of colloquial way I'm thinking about it. In an equation, I would write it like this. You could say the infinite union from k equals 1 to infinity of the bk equals everything, ab. Or you could write it as an integral, which is how we're thinking about things in this course. So you could say the integral of the indicator function of bk equals the integral of ab. Okay, and then the infinite union becomes an infinite sum, k equals 1 to infinity. And this works because they are disjoint. So either way you want to think about it. The infinite union, so unions, if they overlap, then you're counting some things twice. But because the B's don't overlap, you can write the infinite union as an infinite sum, and it's the same thing. Okay. This is the hold on. I wrote the conclusion down, not the. This is going to be the conclusion of the thing. Let me reserve that. What I want just the actual functions, no integrals, just as functions. So okay, the indicator of bk as an infinite sum. Okay, what I said, not what I wrote. Okay, the indicator of bk. So right, if you're somewhere in the bk's, then on this infinite sum you're 1. On the other hand, this is the indicator of the full set. So if you like sets, you would think this way. If you like functions, you'd think this way. They mean exactly the same thing, i.e. this. Okay. Okay, and again, we're not missing any. Any point eventually is in the bk's because any point eventually is less than epsilon over 2, right? So for any fixed x value, eventually you're in the set because you're eventually less than epsilon over 2 b minus a because the limit is 0. So that's why it works. Okay. Questions about that one? Maybe it's a little confusing. Okay. The point is, now we have the no free lunch theorem. The no free lunch theorem tells you when you're in this situation and you have a bunch of sets that go like this, these things are all individually step functions. They are step functions because each of the fn's was step functions. So notice the indicator of bk is a finite union of pieces of intervals, I'll say, of intervals, because the ANs are, indicator of AN is, and that is because the FNs are step functions. So the kind of thing we've been doing, because we started with step functions that have these finitely many pieces, when we say, look at where is the step function less than epsilon over 2b minus a, that will also be a finite union of pieces, and everything is a finite union of pieces. So these things are finite union of intervals. And therefore, by the no free lunch theorem, by no free lunch theorem, this is the big conclusion of why we needed the no free lunch theorem. Then we know the infinite integral is good. So the sum of the integrals, the integral of the indicator of bk, is equal to the integral of the ab, which is b minus a. So in other words, all these pieces converge. Okay, this is the big thing we're going to use. And now, when we have these infinitely many pieces, then that means the pieces individually have to get smaller and smaller. So this is the big thing. This is how we're going to find our n naught. So we're going to let n naught be such that the sum from k equals n naught to infinity, or let's say n naught plus 1 of the indicator of bk, right? So this is the width of the total width of all the pieces except for the first n naught. And this is going to be the tall, skinny rectangle. So we're going to make the first n naught pieces is everything outside the rectangle, and then this red rectangle over here is going to cover the last infinity n naught plus 1 to infinity. This is just like in the warm-up, right? Where we said, look, we had a nice argument for the wide rectangle, and then we're bounding everything in the tall, skinny rectangle. That's the infinite tail. There's infinitely many things, but altogether they are small, okay? That's going to be the red rectangle. So how small do we need this width to be? We need it to be less than epsilon over 2m. It's the width of the red rectangle. So that's what I'm going to pick now. Okay. So this is less than epsilon over 2m. And if you want, this is the width of the red rectangle. Okay. And now everything is set up. We're going to bound the function, and you're going to see that the function fn naught is going to be bounded in the right way by all the things we've set up. It really, the function fn naught really lives underneath both of these two rectangles, and so the area under fn naught is going to be less than epsilon. The area in the red rectangle is going to be less than epsilon over 2. The area in the blue rectangle is also going to be less than epsilon over 2. Okay, I'm about to do that. Any questions or comments about the setup? Yeah.
Can you scroll down?
Yeah.
I was just a little bit confused with the part where you said the indicator function of bk is a finite union of intervals.
Uh-huh. Or I guess bk is a finite union of intervals. The indicator function of bk is a step function.
Okay.
Yeah. So this is important. The theorem we have, the no free lunch theorem, it doesn't work for any function, right? It really works. The functions have to be the indicator of some interval. And it said that if you have the indicator of some interval and you add them up and you get the full interval, then you're good. So it doesn't work for arbitrary functions. It only works for indicators like this. You might complain, I did it with intervals in the no free lunch theorem, and then the indicator of bk is a sum of 10 pieces maybe. So you do have to do some relabeling to make it work. But the point is that this is still an infinite sum of intervals that add up to b minus a. So it's all good. Yeah, that's a good point. Yeah?
Can you just explain again why we can say that sum is less than epsilon over 2?
Yes. Okay. The reason is because this infinite sum is finite. So maybe let's add that in. Since it's summable. So remember, what does it mean when someone says the infinite sum? They mean the limit of the partial sums, right? And if the limit of the partial sums converges, that means that eventually the limit of the partial sums is within epsilon over 2 of the limit, or epsilon over 2m of whatever the limit is. And when it's within epsilon over 2m of the limit, then everything, the whole infinite sequence can add up to no more than epsilon over 2m. Yeah, this is a fact about summable sequences. from like calculus 2 or something. And I guess it's important that everything is positive here. Maybe that helps you see it. And everything is positive. Let's add that in. Great question. Okay. Okay, so here is the bound. And really, again, what I'm really arguing, let's draw the functions one more time. We're going to have the blue rectangle down here in highlighter, the blue rectangle over here, and we're going to have the red rectangle up here. And I'm going to basically argue that the function f lives underneath both of these. Okay, so the function f n naught of x, it's going to live under these two rectangles, and then we're going to take its integral, and its integral will be less than epsilon. And so here's the first step. I'm going to write the function f n naught of x. I'm going to write it as two parts. F n naught of x times the indicator. Okay, actually, let me do this in 3 steps. Times the indicator function of f n naught is less than epsilon over 2b minus a. Okay, this is, I need to zoom in to make this work. Let me start over because I'm out of room already. Okay, we're gonna try to write this equation a little bit better so we can fit it on a line. Okay, f n naught of x, it's equal to f n naught of x times, and I'm gonna put in the number 1, but I'm gonna write the number 1 as a funny way, as I'm gonna say either f n naught of x is less than epsilon over 2b minus a, or it's the opposite. So the indicator of f n naught greater than or equal to epsilon over 2b minus a. And I guess I don't need an x in here. Okay. And if I don't need an x, I can, oh no, I can redraw this a little bit nicer. Okay. So what this is saying is, look, every point in the interval we're talking about, either f n naught is larger than epsilon over 2b minus a, or it's less than epsilon 2b minus a. Those are the only two possibilities. This is just taking this set and dividing it into these two parts. And now I can expand out, and it really is a product of two things. So f n naught of x times the indicator function of f n naught less than epsilon over 2b minus a. Okay, I guess everything is of x. I don't like that. Let's go back and delete the of x. We don't need the of x's. I'm just thinking of functions, not any particular value. Okay, so this is times, and this is times. Okay, plus f n naught times the indicator that f n naught is greater than epsilon over 2b minus a. This is exactly like the proof from the warm-up. We have taken the function f n naught, which has two bad situations. It could be very tall, and it could be very wide, and we're kind of bounding those two sets separately. On this set, where f n naught is less than epsilon over 2b minus a, f n naught, by definition, is less than epsilon over 2b minus a. So this is less than or equal to epsilon over 2b minus a times this indicator, right? So this is bounded by epsilon over 2b minus a. Great, that's no problem. So when f n naught is close to 0, when it's in the blue rectangle, this is the blue rectangle, then the height here is small, epsilon over 2b minus a. Very nice proof. Over here, where it's potentially very tall, I'm just going to bound it by its maximum value, which is m. So I'm going to say plus m. And I'm going to do one other thing. Let me not do one other thing. Let me do things one at a time to keep things from going off the rails. Okay. So I've bounded the function. I bounded it by one height in this set. I bounded it by the other height in the other set. So I'm really doing the picture over here. On parts of it, I bound it by m, the maximum height. On parts of it, I bound it by this epsilon over 2b minus a. So here's the observation now. This set, where fn is bigger than epsilon over 2b minus a, is a subset of the thing we did before. So claim the fn naught larger than or equal to epsilon over 2b minus a. This is a subset of the infinite union going from k equals n naught plus 1 to infinity of the bk. And this is by definition of a n naught and bk's, right? So remember all the way back in our definition, right? We had this chain of things that are getting larger and larger and larger and go up to a minus b. The first a n naught is exactly the set where fn naught is less than epsilon over 2m. So actually this set over here, this is a n naught. And this set over here is a n naught complement. Everything not in a n naught, right? And what is everything not in a n naught? Let's go look at our construction, right? A n naught is somewhere in the sequence. A n naught complement is everything that comes after, is the b's that come after a n naught. It's the infinite union starting at n naught. So this is the whole way the construction was made. And this really is a n naught complement. Maybe that would help like this. And therefore, the indicator function of f n naught greater than epsilon over 2b minus a is a subset becomes a less than or equal to. It's a less than or equal to the infinite sum from k equals n naught plus 1 to infinity of the indicator of the bk. Okay? And now we can do the integral. And because these are intervals, since these are intervals, we can do the integral. Is less than the infinite sum over here. Okay, so in the actual textbook, they don't write these integrals. They write out the sum of all the left-hand side and right-hand side of all the intervals, and it's quite annoying. I like to write it as an integral over here. But the important thing to keep in mind is, like, I couldn't have done this integral trick earlier because it was important that these pieces were all actually intervals where we have the no free lunch theorem. And this thing is exactly what we set up. This thing is the thing that is less than epsilon over 2m by definition of n naught. Okay, so this is lovely. So this is all like a little notice to kind of argue that this term is already going to be small. This term is going to be small because of that. So now I can continue over here. Let's call this heart, just like we had before. And then I say, now notice then heart is bounded by, so we say heart is less than or equal to, okay, it's epsilon, I guess I want the integral of heart. The integral of heart, and let's write it all out. Epsilon 2b minus a times the integral of the indicator of fn naught less than epsilon over 2b minus a plus m times the integral of the indicator of fn naught greater than all this stuff, 2b minus a. And this is less than or equal to epsilon over 2b minus a. This integral, it's definitely bounded by the function 1. The function 1 would integrate all the way up to b minus a. So this is the integral of b minus a. And then the other one is bounded by epsilon over 2m. And we could give this a name as well. We could call this clubs. Okay. I say by clubs. Okay. So the first bit is very short, very wide. The second bit is very tall, but very narrow. And that is epsilon over 2 plus epsilon over 2 equals epsilon. Okay. Therefore, the integral of fn naught is less than epsilon as desired. Okay. And that's the proof. So you catch the two things for two different reasons. In one situation, it's very wide but very short. In the other situation, it's very tall but very narrow. And the narrowness is where we used the no free lunch theorem, said that the narrowness is eventually going down to 0. Okay. Questions or comments about that one? That's a big proof. That might be the biggest proof you've seen in your life. Let's see, how many pages did it take up? It took up like 3 pages because I was writing big. Okay, 4 pages, wow, amazing. In my notes, it was only 2, and I thought I wrote big in my notes, but okay. Questions or comments about any of that? Yeah?
We must have done it last Thursday because, like, I don't even know what the no free lunch theorem is.
Yes, we did it last Thursday, that's right, yeah. So go back, all the lectures are recorded, you should go back and watch the no free lunch theorem.
Oh, they are?
Yes,
Oh, okay.
yes, this is a good pro tip. Yeah?
Right at the end, that last, characteristic function and then
Yeah.
the sum, why is that less than or equal to and not just equal to if those, lower than that?
Oh, this one.
The characteristic function thing afterward. Why is that?
Yeah, you're right, it might be equals. Let me think. I think it's an equal. I think you're right. So this is an equal. I I guess the way, I think maybe this is why it probably survived as a subset. Probably in the textbook, they would say this is a subset of, yeah, you know what? I think it's just more clear. Well, let's write equals. I think that's fine. Yeah, is like literally this. It's equal to this. Oh, maybe you need to do intersect b minus a everywhere. Well, I think that's fine. Okay, I think that's correct. So let's do that. And then yeah, then this will be equal to this. And then everything is still fine. Yeah, that's okay. Yeah, I'm happy with that. Yeah.
You just scroll down a little.
Yeah, for sure. Yes.
To the,
Yeah. Okay. Okay. Fantastic. Okay. So that's like the big proof for today. We're gonna have one little other lemma, and the lemma is taking our big proof and making it a little bit more useful. So our big proof we did says if you're going down to 0, then the limit of the integrals is 0. And then the lemma says that if you're greater than 0, if your limit is greater than 0, then the limit of the integrals is greater than 0. So it's like upgrading from equal 0 to greater than or equal to 0. So we're going to do that. That one will be pretty short and not too bad. So this is lemma 2.3.2. Okay, and let me copy down the statement correctly over here. This is the normal free lunch theorem. This is this. Okay. Let me read this proof and see if we actually have time to do this. Maybe this is harder than I thought. I was thinking of this one being, okay, this one I would say is medium difficulty. Okay, all right. So the theorem says if f is equal to f1 plus f2 plus dot dot dot, and f is greater than or equal to 0 pointwise, so it's greater than 0 for every single value, then the infinite sum, the sum from k equals 1 to infinity of the integral of the fk is also greater than or equal to 0. So these are step functions over here, step functions. So this is the thing that we were doing. Okay. Now I'm nervous that I like skipped a proof or something, but I think, yeah, see, I did skip one. Okay, great. This will be some other time. This one is medium difficulty, and we'll do it some other time. The one that we want to do is this one. Sorry for people who already copied down. Corollary 2.2.7, which we'll do this one, and then we'll be done. So it says, let Fn be weekly increasing sequence of step functions. So this time they're going up, and we know that the limit is greater than or equal to 0. The limit as n goes to infinity of the Fn of x is greater than or equal to 0. This is for all x. So they go up, and they end somewhere positive. That's what we know. And the conclusion is that the integral of the limit is also positive. Then the limit as n goes to infinity of the integral of Fn is also greater than or equal to 0. So the functions eventually become positive, well then their integrals also eventually become positive as well. Okay, and it is this proof involves a nice new notation that you've maybe never seen before, which is we split a function into its positive and negative part. Split a function into its positive and negative part. Okay, and I will draw you a picture of what this looks like. So if you have some function over here, here's my favorite function. It looks like that. Okay, you can cut it into the parts where it's positive and the parts where it's negative. So the positive part will look like this. It'll be like flat and then like this. Okay, this is the positive part of the function. That is called f plus the positive part of the function. And the negative part of the function it's all the negative stuff. It's like this. Okay, So it's flat and then like this. For whatever reason, the first person who ever did this didn't define the pink thing to be the negative part of the function. They said that that is the negative of the negative part. So send them an angry email. That's f minus. So the function f, the original blue function f, it can be written as its positive part minus its negative part. Okay, and the positive part is the part where it's greater than 0. The negative part is the part where it's less than 0, but with a minus sign. So the negative part of the function is actually positive, is actually this thing, right? It's like the parts where it's negative but flipped. If you want an actual definition, I can give it to you. F plus is equal to the maximum, whichever is bigger, f and 0. Okay, and f minus, the negative part, is negative f minus. Yeah, okay, I'll write it the way, this is the way the textbook writes it, which I don't like, but that's what we're gonna do. It's the maximum of negative f and 0. So if f is negative, then negative f is positive, and then you're doing the maximum of the positive number and 0, you get the positive number. So that's where the negative sign is. So that's f minus and f plus are the, you do some weird combination of maxes to get what you want, but this is like the picture. So f has the parts of where it's positive and the parts where it's negative. Okay, what are we told about our step functions? Oh, okay, here's an important observation before we do anything else. Fn is a step function. Fn is a step function, and therefore Fn plus and Fn minus are also step functions. So remember, you have intervals where it's positive or negative. If you do this thing on a step function, you're just going to get 2 step functions for the things. And so we're basically going to apply our theorem that we just proved to Fn plus and Fn minus and get it. What are we told about our things? We're told our functions are eventually positive. And I claim that if we're told that the functions are eventually positive, that means the negative part is eventually 0. Okay? So limit as n goes to infinity of Fn of x greater than or equal to 0 implies the limit as n goes to infinity of Fn plus of x equals 0, right? Nope, the negative part is 0, okay. The negative part is 0. So the functions are going up, 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 they're eventually positive, which means that eventually their negative part sort of vanishes and they're only left with their positive part, okay? And by the theorem applied to, by the theorem we just proved, applied to the sequence of negative parts to the negative parts, f1 minus f2 minus ... So the sequence of the negative parts, that is having an integral that is converging to 0. We have that the integral, the limit as n goes to infinity of the integral of Fn minus equals 0. Right? So the Fn minuses, they're going to 0 pointwise, they're all step functions, and therefore their integral is going to 0. And so if the integral of the minus parts, the negative parts, is going down to 0, then what's left? Well, the integral of the function f will be the integral of the positive part, and the positive part is always greater than 0. So it's going to be greater than 0. So we just got to do a little chain of inequalities here at the end. So now consider Fn equals Fn plus minus Fn minus, and therefore we can do the integral of both sides. This is okay for step functions, which is something we've proven. This is okay for step functions. That was a lemma that we did a while ago. Okay, and if I take the limit as n goes to infinity of the integral of Fn, that'll be the limit as n goes to infinity of the integral. Do I want to do the integral first, or I just want to say it's greater than 0 first? Let's make it greater than 0 first. Yeah. This is greater than or equal to 0 minus the integral of Fn minus. And now I'll take the limit of both sides. The limit as n goes to infinity of the left-hand side is greater than or equal to 0 minus the limit as n goes to infinity of the integral of Fn minus, which is equal to 0 minus 0, equals 0. Okay. So in other words, these things are going to 0, and so the whole thing is positive, because you're basically left with the positive part of the function. Because it's positive, its integral is positive. Okay. Questions or comments? About that one? Yeah, that one's not so bad. This positive, negative notation will come up later as well as a common way of dealing with these functions, because you know when it's positive, when it's negative, you can handle these inequalities kind of nicely. Okay, so very technically, where are we in the course? We've finished section 2.2. So where are we? We have finished 2.2. Section 2.3 starts with the definition of the Lebesgue integral, which is we've already done a little bit with, but we have to now go finish. Next up is finish the technical theorems. Technical theorems from 2.3. Okay, so and that's what's listed over here, way at the beginning of what I planned to do here. So we've done this one. Lemma 2.3.2 is greater than or equal to 0. It's essentially what we just did. And then once you have that one, you get this corollary. I think my plan is I'm going to put these ones, here's what we're going to do. The Thursday to Tuesday video, because it's the break, there won't be a quiz or anything like that. On Tuesday, maybe I won't commit in case there's a problem. No, I should commit. Okay, Tuesday we'll have a regular lecture. So no problems on Tuesday after the break, so you guys can have a nice break and not have to study or anything. I'll put the proofs of these things in a video, but it'll be like an optional video. So you can watch it. The proofs are pretty technical. You could also read them from the textbook. And really, we've done all the hard ideas. So doing theorem 2.2.6 like we did today, and the no free lunch theorem, those were the real ideas. This is some sort of technical bookkeeping to turn what we had into these things, and it's not so complicated. And then we'll be able to start playing with this L1 space when we get back from the break. Okay, so that's the plan. Any questions or comments? Okay, let's finish a little bit early, and have a really good break. Enjoy yourself, and we'll see you well rested in 1 week.